Hello, we are Group 13. This is prepared by Vic, Ronak, Sebastian, and Rishab. I'm Sebastian, and together we're going to look at a study of the factors that are most important to whether a baseball pitch is hit or not. As a background, team invests millions in players' development, scouting, and analytics to understand exactly what pitch characteristics like velocity, pitch type, rotation, sequence, context, and fatigue increase the likelihood of pitches being hit. Previously, once considered underdog teams challenged traditional scouting by prioritizing analytics. Nowadays, today's front office, broadcasters, fantasy baseball players, and fans are all captivated by this data to predict wins and secure bets. For scouts, this information can help identify undervalued pitchers, respond mechanic flows. For coaches, it can help guide the pitch strategies or whether to pull a starter. For fans and analysts, it can help a deeper understanding of the game, hidden layers, and for players, it can help guarantee longevity. The general question is what are the most important factors that influence whether a pitch is hit or not? For my research questions, I am analyzing do pitch type, launch angle, barrel percent, and release speed significantly impact the launch speed of a bat. Understanding launch speed is critical for improving player performance and offensive strategy. Launch speed significance shows that launch speed is the best predictor to determine how likely a ball is to become a hit. Higher launch speed means a higher chance that the ball will become a hit and it will be harder for the fielder to recover or will become a home run. The study objective is to examine key predictors to quantify the strength and direction of each predictor's relationship with launch speed and to provide actionable insights for hitters, coaches, and analysts to enhance offensive behavior. My research question is does pitch type, launch angle, barrel percent, and release speed significantly impact the launch speed of a batted ball? The null hypothesis is that there is no significant relationship between pitch type, launch angle, barrel percent, release speed, and launch ball, which means H naught, beta 1 is equal to beta 2 is equal to beta 3 equals beta 4, which is equal to 0. And the alternative hypothesis is that at least one of the predictors significantly impacts launch speed, which means that at least one beta k equals 0 for k is 1 to 4 does not equal 0. Look into my dataset, which is from the StatCast 2024. The first variable is launch speed, which is the speed of the ball at the contact of the bat, which is the quantitative one, as well as the response variable. The next variable is launch angle, which is the vertical angle at which the ball leaves the bat after contact in degrees, which is the quantitative. The third one is barrel per percent, which is the percent of batted balls classified as barrels, which means optimal exit velocity, and angel, which is quantitative. Fourth is pitch type, which is the 7 different types of pitch type, which is categorical. And the last one is release speed, which is the speed of the pitch when it leaves the pitcher's hand, which is also quantitative variable, and we're not being treated as dummy variables. Now we're going to go into the model diagnosis and exception checking. The first part being multicollinearity, which we can use the VIF to show. This shows the highest G VIF was 2.06, which is well below the concern threshold of 10, showing that multicollinearity is not a problem. The second part is the heteroscedasticity test, which shows that the p-value using the Braunschweiger test is way too high, meaning that we're going to have to use the WLS to correct our mistake. Looking into the second part, we're going to look at the normality of residuals, which is the Shapiro and Gugu plot. And after looking at them, it is clear that a box cost transformation or robust regression should be applied to improve the model diagnosis and ensure more accurate prediction intervals. Next, we're going to look at the outlier analysis, which, after looking at the figure, it is clear that no immediate action is needed because there are no strong outliers. The influence analysis, looking at Cook's distance, shows that all Cook values were small and below the 0.5 threshold, showing that no action is needed. Lastly, looking at the leverage hat values, it's shown that two observations showed high leverage, which is approximately 0.05, showing that we're going to need to take a look at the original model and add an interaction effect to solve that high leverage hat. As a summary, there are three things we need to address: heteroscedasticity, non-normal residuals, as well as high leverage points. So moving into the model adjustment action, first looking at heteroscedasticity, we have to use weighted least squares, where after doing so, the WLS reduced the residual spread, increasing barrel speed by P 0.048, as well as it significantly raised the 0.34 mile an hour with other predictors showing it's weaker at a 10% level. Next, we're going to go to the non-normal residuals, where we use the ridge regression, which shows that ridge regression stabilized coefficients with a reference intercept of approximately 7 miles an hour. EVIS had a strong negative effect, while launch angle and barrel percent and release speed showed small positive impacts. Lastly, looking at the high leverage points in the model adjustment, we have to show that restricting for the full model, launch speed is approximately pitch type, launch angle, barrel percent, release speed, to the interaction model, which now takes launch speed and uses pitch type multiplied by the three continuous variables, which improves the adjusted R squared from approximately 0.045 to 0.066, indicating a strong positive predictive accuracy. This interaction effect allows the pitch type to interact with those three continuous variables. So we're going to implement a stepwise regression refinement, which is going to improve model simplicity and performance by removing weak interactions. Looking at the results after we've implemented it, it removed the interaction between barrel percent and release speed, retained only pitch type time launch angle interactions, the final adjusted R square, which is 0.03811, but the AIC was improved by 29932. Looking at the outcomes, it shows a stronger model personally with minimal loss of explanatory power. The launch interactions remain statistically significant, and diagnosis confirmed no multicollinearity or influential power point. Moving into the validation, we use a k-fold cross-validation, which confirms that the stepwise interaction model generalizes well with consistent performance on both training and unseen data. The 10-fold cross-validation uses 9% training and 10% validation across this folds. Looking at the performance metrics, you can see the training RSME was 14.62, the training R-squared was 0.0355, and the validation was RMSE was 14.56, and the validation MAE was 11.75, and the validation adjusted R-squared was 0.038, which shows that there were small differences between the training and validation performance, no evidence of overfittings, and the model captures meaningful relationships despite low overall R-squared, which is to be accepted because we're using complex sports data, and this aligns with other R-squares with similar data sets. Now bringing it back to the summary of the key findings of launch speed, which shows that both pitch characteristics and batted ball's quality significantly influence launch speed. Looking at the categorical predictions, which is pitch type effects, it shows that EVIS pitches significantly reduce the launch speed coefficient negative 25.64 and p is equal to 0.028. Sinkers significantly increase the launch speed with the coefficients of plus 1.24 and a p of 0.036. And all other pitch types show no statistical differences from four-seam fastballs. Look at the categorical predictors pitch type effect. You can see that barrel flip percentage is the strongest predictor with the coefficients of 0.35 with the p very, very small, and it increases the launch speed by approximately 0.35 miles an hour. The launch angle has a positive but small effect with the coefficients of 0.0155, and then the release speed also has a positive impact, showing 0.1432. And looking at this interpretation, this makes sense that well-struck balls and optimal launch positions enhance exit velocities, and these findings align with the baseball intuition that quality contact and pitch dynamics drive positive offensive outcomes.
Our second research question is, does the effect of pitch type and the effect of pitcher's age impact a pitcher's fatigue levels?
In this question, we try a confirmatory observational study. So we try to test previous studies that claim, for example, that fastballs are more fatiguing due to higher mechanical tension, or that older pitchers tend to have lower fatigue levels because they try to conserve energy and are aware that fatigue is more limiting to older pitchers. And the second thing we want to study and validate is that age and pitch type actually explain a significant portion of variability in pitch scores, as through the research, it seems like those are the two greatest indicators. The null hypothesis says that pitch type and age have no effect on fatigue. So we claim that all the coefficients, both of the age and the dummy variables for pitch type and slider and pitch type sinker, right, are zero. And the alternative hypothesis says at least one of them are significantly contributing to the effect on fatigue. In doing so, we create the pitch type fastball as our baseline for our dummy models. Okay, so these are our variables. What you want to look out for is that fatigue score is actually defined as a composite score of a bunch of different variables, such as in the research for defining fatigue score, we found that lower release speed, higher run value per 100 pitches, and barrel percentage were all like used by other research to claim fatigue, right? So, and like mimic the fatigue score. Our initial model showed all predictors were highly significant. Pitchers throwing sliders tended to have higher fatigue scores, seen in the code, and older pitchers also showed increasing fatigue, seen in the chart. Also, the model explained about 36% of the variance. In our initial OLS model, we saw non-constant variance and strong non-normality. So we ran a Box-Cox transformation, and normality seemed to improve, and specifically also variance seemed to improve a lot. So in trying to improve the non-normality of the Box-Cox transformation, we tried the WLS model, which did actually increase variance a lot, but decreased normality quite a bit. And same for the ridge regression model, right? So to get like the balance of both worlds, we ended up choosing that the Box-Cox transformation was good enough to have not completely significant normality nor variance issues. After our Box-Cox transformation, we saw 4,500 influential points by Cook's distance. If we just outright remove them, many influential points were rare combinations of pitch type and age. So instead, we tried on like robust modeling, right, using robust regression. But in doing so, we just confirmed coefficient robustness, and we didn't end up using our robust model because the residual standard error increased. So now we were able to run subset selection on our confirmatory model. Because these were all covariates, we couldn't end up eliminating any of them. But surprisingly, we didn't have to because all criteria, adjusted R-squared, MALOCP, and SBC favored the full model. We k-cross validated our now just transformed Box-Cox model, and we found a root mean squared of 4.653, R-squared of 1/3, and mean absolute error of 3.75. Right, so there was reasonable predictive accuracy in our root mean squared error, accounting for like the Box-Cox transformation, and that also our model explains just with two additive variables 33% of our variability in fatigue scores. So to conclude, we can reject the null and claim that both predictors are of great importance for measuring fatigue, right? We can also say that sinkers and sliders are associated with greater fatigue levels as compared to fastballs when controlling for age, which goes against past research. And older pitchers generally have higher fatigue scores, which also goes against past research. So then on the same topic, we asked research question 3, does the effect of pitch type on fatigue depend on the pitcher's age? So our motivation for testing the interaction is that the last question was really just revealing that both pitch type and pitcher age independently contribute to fatigue. But an older pitcher might find themselves significantly more fatigued to throw a slider as compared to like a younger pitcher, right? So in this way, we actually want to see more actionable insights by constructing an interaction model, right? And this is also a confirmatory observational study. Our null hypothesis was that there is no interaction between pitch type and age on fatigue, and our alternative is that there is an interaction and that the relationship between pitch type and fatigue changes depending on the pitcher's age. So we now add one more variable, pitcher age and pitch type, which defined as how the pitch type's effect on fatigue changes with differing age. So running a partial F-test, before that, we actually centered age variable to reduce multicollinearity in the interaction model. But when running the partial F-test, all main effects and interaction effects were still statistically significant, right? And that the partial F-test indicated that interaction terms actually improved model fit. After running the tests on the initial OLS model, we saw that there was non-constant variance and non-normality. So again, we tried the Box-Cox transformation and found that there was slightly better normal residuals. And then after running the robust regression model, we saw a slight improvement, but on the QQ plot, there was still minor tail deviations. So we ended up sticking with our Box-Cox transformation to have, again, like the best of both worlds for variance and normality. We again saw 4,500 influential points, and rather than just taking them out, for example, if we did, many of them were from older pitchers throwing sliders or sinkers, and that would cause a decrease in some interaction effect group, in these interaction effect groups. So rather than doing that, we decided to keep all of the data and rely on robust regression if needed, right? If our model didn't work out correctly, but ultimately we just stuck with the Box-Cox transformed OLS. Also note the reason why we didn't choose the robust regression model is that it was more of a confirmatory to show that our predictions for OLS and robust regression were actually practically the same. And much like research question 1, the residual standard error also increased. So therefore, we chose the Box-Cox transformation. At first, we saw some multicollinearity issues, but when centering and standardizing the x values, we saw that all VIF values decreased below 2, so no flags for multicollinearity remained. It was confirmatory, so we couldn't take out any of the interaction effects anyways, but we still ran stepwise selection and found that actually our full model had the lowest AIC. And so also comparing AIC of the previous main effects model and that of the interaction effects model, which you can see in the picture, we saw a great significant drop in AIC. Our k-fold cross-validation metrics also got much better in terms of root mean squared error and mean absolute error. The reason why we can say that is because even though we're comparing Box-Cox transformations, both of them were square root transformations, so they should be similar. And also that our interaction model slightly captures less variance, but that could also be because interaction could be weak relative to the overall noise. Thus, even though there was no R-squared increase, there's still meaning for interpreting the interaction effect through the f-test and model selection. Right? For example, older pitchers may experience greater fatigue when throwing sliders, suggesting pitch selection could be age-dependent.
Hey everyone, my name's Ronak and I'm going to be presenting to you research question number 4. So this is going to look at whether a pitcher's dominant hand affects hit quality as measured by exit velocity or speed off the bat. Specifically, we just wanted to know if right-handed or left-handed pitchers cause differences in how hard the ball is hit after contact. Now, our null hypothesis was that the pitcher's dominant hand would have no significant effect. So conversely, the alternative would be that the dominant hand of the pitcher would actually significantly affect the exit velocity. Now we use StatCast data for a week of the 2024 MLB season from this study. As you can see, I included a screenshot of our data set over here. Our response variable was launch speed, also known as exit velocity, measured in miles per hour. And our predictors included throwing hand, pitch type, and release speed. Now, throwing type was our primary predictor because that's what we're trying to find out. And then pitch type and release speed were more control variables. This was also set up as an observational study, and we fit a multiple linear regression model to test the relationships. So looking at our results, we checked our model assumptions. The Shapiro-Wilk test showed slight non-normality, but that's expected with a large data set. The Bruges-Pagan test detected there was heteroscedasticity, meaning the variability of the errors was not constant. And we also ran the Cook's distance, and that showed there were no highly influential points and no observations had an outsized effect. Everything was below 1, probably due to it being such a large data set. Not one point is going to have a really big impact. So now when we look at the model results, the p-value for the throw-in hand was 0.338, which is a lot higher than the significance level, meaning it was not statistically significant. However, the global f-test did show the overall model was significant, meaning at least one predictor, it was probably pitch type or release speed. That actually does have something to do with exit velocity. And like I said earlier, because we needed to fix our heteroscedasticity, we used ridge regression to stabilize the model. And bootstrapping intervals confirmed that the throwing hand still had no effect on exit velocity. Now, looking into discussions, limitations, and improvements. Obviously, like I said, our findings suggest that a pitcher's dominant hand does not significantly impact how hard the ball is hit. Instead, pitch characteristics like we found, like maybe pitch speed or the movement of the ball, like whether it's a fastball, slider, curve, changeup, those play a bigger role. One limitation of our study was we only focus on exit velocity, not outcomes such as batting average or home runs. So if you want to determine like what's the best hit, the highest miles per hour off the bat might not be the best. It has something to do with the launch angle, and there's more factors with that. So for future research, it would be interesting to look at. I know something I found cool would have been if batter-handedness interactions made a difference. Like if it was a righty batter, are they better against lefty pitchers, or a lefty batter, are they against righty pitchers? Just depending on that. And then also include some other predictors like spin rate and pitch release point that would give our model a more accurate suggestion.
The fifth research question is, does the pitcher's role as a starter or reliever affect the runs allowed by a pitcher after taking into account their age and highest release speed? The null hypothesis is that starters and relievers allow the same amount of runs to be scored against them when taking everything else into account. There are 4 variables used in this analysis. 3 of them are continuous, and 1 of them is categorical. This is taken from the same dataset as the previous research questions we're using, though it is clubbing data by pitcher rather than by single pitch. The regression was built with the run value per 100 being predicted by the age of the player and the max pitch speed. This failed the global F-test with a p-value of 0.1, and it also failed the Shapiro-Wilk test with a p-value much less than 0.05. Histograms of the distribution within each variable. They're all fairly normal, except age is slightly skewed to the right, and it's visible that the categorical variable starter has about twice as many relievers as starters. The residual plots are showing some nonlinearity at the tails of the Q2 graph, and many issues in the scale location graph. To resolve the nonlinearity issues, we tried the Box-Cox transformation. The process is shown here, but it did not significantly improve the p-value or the nonlinearity issues. To try and remedy it further, we tried to remove the outliers with the box plot. They did significantly improve both the F-test and Shapiro test, and both of them passed. The starter variable is also added to the regression. It passes the global F-test, but it failed multicollinearity test. So removing the interaction terms which are causing the issues, we were able to regress again and pass the global F-test and multicollinearity. It also should be noted that the p-value is strongest with the starter variable, so it does seem to be that we can reject the null hypothesis. Residual and influential point plots with significant improvements on the residual plots front, and only a few minor points of influence seen at the right plots. For the model validation, we opted for the best subset approach. The 3 it suggested had very similar AICs, and we opted to keep the model with the starter and max speed variables included. With the K-folds, we were able to see that it does have a low R-squared value, but also it has quite low MSE and RMSE values. Sufficient evidence to reject the null hypothesis, and we can say that starting pitchers allow about 0.79 runs fewer per 100 pitches than relievers. We could potentially expand on this analysis by looking at further time periods, and it could be interesting to see how many of the 0.79 runs come from the fact that batters could already be on past bases by the time relievers are able to come on to the pitch.